This video is on manometer as a supplement to lecture 2. Let's assume the manometer fluid has the density of rho F and fluid 1, which is in the left leg, has got the height of D1 and fluid 2 has got the height of D2. Therefore, D1 minus D2 is equal to h, the difference in height, which we have here. The pressure here is P1 and here is P2. We would like to develop a relationship for P1 and P2. So we assume 2 points. One of them is point A here and the other one is point B here. Since point A and point B are at the same level and they are connected by manometer fluid, therefore PA is equal to PB. Now we can formulate the pressure exerted in point A. So PA would be equal to pressure P1, which is on top of it, plus the hydrostatic pressure in height D1, which will be equal to rho 1 G over GC D1. PB, which is the pressure at the opposite point. B has got 2 fluids on top of it plus pressure P2. Therefore, PB would be equal to P2 plus the hydrostatic pressure rho 2 G over GC D2 plus the hydrostatic pressure due to column H. Column H is manometer fluid, so rho F G over GC H. And if we equate these two, because PB and PA are equal, then we will have the general equation for manometer as P1 plus rho 1 G over GC D1 equals to P2 plus rho 2 G over GC D2 plus rho F G over GC H. This is the general equation for manometer that we're going to use for specific cases. The first case that we consider is a differential manometer. What is that? This is a manometer connected to a pipe where a process fluid is flowing. Therefore, this column and this column are filled with process fluid which is in the pipe. Let's assume the density of process fluid is rho. Here we have the density of manometer fluid as rho F, and here we have the difference in height H. If we apply the general equation here and want to get the difference between P1 and P2, you may know that as fluid flows through a pipe, the pressure will drop. Therefore, P1 is bigger than P2, and it shows on the differential manometer because this level is lower than that, so it has pushed the manometer fluid down. P1 minus P2 equals to rho F G over GC H plus G over GC rho 2 D2 minus rho 1 D1. And since rho 2 and rho 1 are equal and they are equal to rho, they can come outside the parentheses. Also, this is D2, this is D1. D2 minus D1 is minus H. P1 minus P2 is equal to rho F G over GC H minus G over GC rho D1 minus D2. And this is equal to H. If we factor out and simplify, we are going to get an equation for differential manometer as rho F minus rho G over GC H. a general equation but for differential manometer. So let's write the equation for differential manometer we just derived here. Rho F minus rho G over GC H. This is height H, this is height H, and that is height H. In the open-ended case, manometer is connected to P1 inside the pipe, but the other side is open to atmosphere, therefore P2 is equal to P atmosphere. If we apply the equation, that would give us P1 minus P atmosphere equals to rho F minus rho G over GCH. This reading will be gauge pressure, and open-ended case will read gauge pressure inside the pipe. Differential is the same as we just talked, P1 minus P2, and the sealed end has got P2 equal to 0 because here is vacuum. In that case, P1 minus 0 would be rho F minus rho G over GC H. The reading would be an absolute pressure, not like the first one, which was the gauge pressure. So as you see, we can read gauge pressure, we can read absolute pressure or differential pressure depending on different cases of connecting the manometer to a pipe. Let's do some exercise here. We would like to convert 5 psia to millimeter of mercury. From the conversion table in the beginning of the book, we will read conversion of millimeter of mercury to psia, 5.0 psia, and the conversion is 760 millimeter of mercury is equivalent to 14.696 psia. This will give me 258.573, and the last digit is here because of 5.0. If I round it off, I will have 259 millimeter of mercury. Next one, 20 inches of water head, we want to convert it to psia. We know P1 minus P2 is equal to rho of water G over GC H, 62.43 pound mass of water per foot cube. This is the density rho. G over GC is 1 pound force per pound mass. And H has been given as 20 inches. But I have foot and inch, I have to convert. So here I will have 1 foot cube to 12 inches cube. This foot will cancel out, one of these inches will cancel out one of these inches, and we will be left by inch square. So pound mass cancels out, so the result would be pound force per square inch, which is psi, or and since this is absolute, so that will be psia, and the result would be 0.7225. The last digit is 2 because of the 20, therefore I will have 0.722 psia. Actually, we will have 7.23 psia. Next, 10 foot of methanol to mercury. Let's look up the specific gravity of methanol as 0.792. Specific gravity of mercury 13.546. I have rho HGG over GC H that is a column of mercury. I want this to be equivalent to a column of methanol. G over GC cancels out, so I have a relationship when I want to convert one column to the other. Rho Hg, Hg would be rho of methanol, H of methanol. So what is unknown here is column of mercury, but the column HM is already 10 foot. H of Hg would be equal to rho of methanol, H of methanol divided by rho of Hg. I have the ratio of densities. The ratio of densities would be the same as the ratio of specific gravities. So therefore I have 792 for methanol divided by 13.546 for mercury. And then I have 10 foot of methanol, but I want the height of mercury in millimeter, so I need to do a conversion of foot to millimeter, and as a result I will have 178.2 with significant digit. Last one is this one, rounded off, 178 millimeter of mercury. We have a problem that is given in the exercise that we would like to do. In here I have a barometer which has got the same fluid in it as the manometer fluid. This will help me to get the density of manometer fluid. Here is vacuum, so pressure at that point is 0, and pressure here is atmospheric pressure. This is how a barometer works. So for the barometer, P atmosphere minus 0 would be equal to 10.02 height of manometer fluid, which has got the density rho f. And in the problem it says that atmospheric pressure is 754 millimeter of mercury. 754 millimeter of mercury is equivalent to 10.02 foot of manometer fluid with density rho f. I can get the density from here because I can write rho of manometer fluid times 10.02 in foot, of course. Manometer fluid, we learned that this is equal to rho Hg times the column of Hg, which is 754 millimeter of Hg. Of course, the units have to be made consistent. Rho f equals to 13.546, which is the specific gravity of mercury, multiplied by 754 millimeter of mercury divided by 10.02 foot. I have to make a conversion of 1 foot here over 304.8 millimeter. So foot cancels out and millimeter cancels out. I have to multiply it by 62.43, which is the density of water pound mass per foot cube. This will give me rho f in pound mass per foot cube. This will be equal to 208.782, and the last significant digit would be 7. This is in pound mass per foot cube, density of manometer fluid. With the manometer fluid as we found, we can write the equation for differential manometer as P1 minus P2 equals rho f minus rho, and in here rho is the other fluid in the legs, which is water, so this is rho of H2O. G over GC, delta Z, and delta Z is given as 20 inches. So P1 minus P2 would be equal to 208,782 minus rho of water is 62.43. Both of these are pound mass per foot cube. G over GC, 1 pound force per pound mass. And delta Z is given as 20 inches. So here is 20 inches. But we have to convert foot and inch. I will have 1 foot cube over 12-inch cube. And in here, foot cancels out. One of these inches with this will make inch square. Pound mass cancels out. I will be left with pound force per inch square, which is PSI. This is differential pressure, so we may write PSI or PSIA. The answer would be 1.69388. Last significant digit would be this one. Therefore, rounding off, 1.694 PSI or PSIA really doesn't matter, because in this case it's differential pressure.